Hey everyone, I'm Dmitrii Ivashchenko from Games, and today we are diving into Trio, a super cool Python library for synchronous programming. We are going to break down how Trio uses its neat structured concurrency model to manage tasks. I'll walk you through some practical examples that you can start using right away in your projects. So let's get started. Alright, let's dive into how Trio works. First, we'll explore Trio's structured concurrency, which makes your code cleaner and easier to manage. We'll examine how Trio handles timeouts and cancellations, ensuring tasks don't hang and waste resources. Additionally, we will look at how Trio syncs tasks and manages our operations to keep things running smoothly. Then we will see how Trio stands out compared to Asyncio, focusing on its core functionality. We will discuss the Trio Asyncio library for mixed environments. Lastly, we will cover Trio's latest updates. So let's dive into the details. Let's start with Trio core features. And the first thing we'll start with is nurseries and spawning. Nurseries and spawning enable managing multiple asynchronous tasks concurrently. They are core to Trio's design for handling concurrent operations. This mechanism ensures that tasks are executed in a structured and controlled environment. Tasks within a nursery will start, execute, and terminate together, maintaining a clear life cycle. Let's look at how you can actually use nurseries in your code. The syntax for using nurseries in Trio involves the async with statement. We begin by calling trio.openNursery to create a new nursery context. Within this context, you can spawn tasks using nursery start soon. This example shows a simple parent-child task stop. The child task runs concurrently, and the nursery ensures all tasks complete before exiting. With that syntax in mind, imagine applying it to something like handling multiple web requests simultaneously. Using nurseries, each web request is treated as a separate task. The nursery manages these fetch tasks, starting them almost simultaneously and ensuring all are completed before the application continues. Such a setup is ideal for improving the responsiveness and throughput of web applications. Moving on from nurseries, let's talk about another key feature, checkpoints. Checkpoints in Trio are critical for managing task transitions effectively. They serve dual purposes, checking for cancellation and allowing task switching. This ensures responsive and robust asynchronous applications. By integrating checkpoints, Trio helps maintain a cooperative multitasking environment. To give you a clearer picture of how checkpoints work, let's break down what happens during a typical async operation. Checkpoints occur every async operation that potential blocks, like await trio.sleep1. A checkpoint allows Trio to check if the task should be cancelled. It also lets the Trio schedule decide if it's time to switch to maybe another task. These points are essential for maintaining fairness and responsiveness in the system. Now let's see how these checkpoints play out in real life. Consider an application that manages simultaneous database queries. Using checkpoints effectively allows each query to run concurrently. This minimizes response times and maximizes efficiency. For instance, while one query is waiting for data, another can proceed. Proper use of checkpoints ensures that no single task hogs system resources. Moving on, it's important to talk about error handling. In Trio, multiple tasks can fall simultaneously, and this can lead to multiple exceptions being thrown at once. So Trio uses exception group to encapsulate these exceptions. This model allows handling several exceptions together efficiently. Trio supports Python except syntax, so version 3.11 for handling exception groups. Each type of exception within an exception group can be handled separately. This allows for precise control over error handling in concurrent environments. It's an essential tool for developers to manage errors in multiple concurrent tasks. To see this in action, imagine managing file operations where things might not go as planned. Using trios, error handling, both read and write errors are managed concurrently. If errors occur, they are encapsulated in an exception group. This allows handling errors from multiple operations in a single block. Alright, switching gears a bit, let's talk about timeouts. Timeouts in Trio control how long a block of code is allowed to run before it's cancelled. They are implemented using cancel scopes. This provides a straightforward way to handle operations that should not run indefinitely. Using timeouts, you can prevent resources from being tied up by tasks that take too long, maybe. Here is how you can practically set these timeouts to keep your operations smooth and efficient. The moveOnAfter function sets a timeout for the enclosed block of code. If the code inside a block takes longer than the specified time, it is cancelled. Cancellation is achieved by erasing a cancelled exception within the block. It's a simple yet powerful tool for controlling task execution times. So imagine you're running a busy web server that must manage a high volume of incoming requests. Setting timeouts ensures that no single request can overwhelm this server. This example uses a 5-second timeout for each request. If processing exceeds this limit, the server responds with a timeout message. Implementing timeouts like this can significantly improve server reliability and responsiveness. Now let's pivot to another critical feature, cancellation. Cancellation in Trio is a mechanism to stop tasks explicitly or due to timeouts. It utilizes a structured approach to handle task interruptions effectively. This feature integrates into Trio's concurrent programming model seamlessly, and it offers developers control over the lifecycle of asynchronous operations. Cancellation ensures that resources are not wasted on tasks that need to be halted. Let's dive deeper into how you can set up these cancellations within your tasks for cleaner control. Trio uses trio.moveOnAfter to define a timeout for task cancellation. If task exceeds the timeout, Trio raises a cancelled exception. This exception unwinds the execution stack and stops the task cleanly. Developers should handle this exception to clean up resources properly. For a practical scenario, consider managing database transactions with cancellation. Setting a timeout ensures that transactions do not hang indefinitely. Here we have a database query with a 3-second timeout. If the query exceeds this limit, the transaction is cancelled. Using cancellation in this way helps maintaining application stability and responsiveness. Moving on, let's see how Trio organizes task communication and synchronization. This part is key for maintaining order in your apps. Trio provides a powerful tool for task synchronization and inter-task communication. These tools are essential for managing state and coordinating concurrent operations. They are designed to be both efficient and fair, ensuring no tasks are unfairly delayed. A great tool for this is the semaphore. A semaphore is used here to manage access between concurrent tasks. Tasks require a semaphore to ensure exclusive access to resources. This pattern prevents race conditions and ensures tasks operate in the correct sequence. Each synchronization object in Trio is designed to be fair, allocating resources in the order requests were made. Another powerful pattern is the producer-consumer model. This example illustrates using channels to pass messages between tasks. A producer sends a series of messages to a consumer via a memory channel. Channels ensure that messages are passed safely and efficiently between tasks. The consumer processes each message as it arrives, maintaining flow control. Using channels helps prevent data loss and ensures that messages are processed in the order they are sent. Speaking of channels, let's shift our focus to another Trio's feature, working with streams. Trio's I/O capabilities center around an abstract stream API for byte streams. This API makes it easier to create flexible and reusable protocol implementations. By abstracting the stream interfaces, Trio allows for a variety of data transport mechanisms. For instance, setting up secure encrypted connections is straightforward with Trio. We can use an SSL stream wrapped around a socket stream. Here we set up an SSL connection over a standard TCP socket. SSL stream abstracts encryption by making the underlying transport mechanism interchangeable. Trio's approach makes it easier to adapt existing code to support secure connections without significant changes. Trio also provides robust support for asynchronous file system I/O. This example shows asynchronous file reading using the path object in Trio. Asynchronous file operations prevent I/O operations from blocking the main thread of execution. This technique significantly reduces latency in I/O-intensive applications. Having seen all these features, let's put Trio side by side with Asyncio and discuss the differences. The first thing that catches your eyes is the structured concurrency model. Trio and Asyncio offer distinct approaches to handling asynchronous operations. Trio employs nurseries for structured task management, enhancing readability and safety. Asyncio relies on an event loop and futures, which can be more flexible but harder to manage. In Trio, asynchronous tasks are managed within nurseries, providing explicit scoping. The syntax highlights the hierarchical structure of task dependencies. Asyncio utilizes an event loop where tasks are managed through futures and callbacks. We can see how each model influences error handling and task lifecycle management. Consider a web server designed to handle multiple simultaneous requests. In Trio, each request is a task executed within a nursery, ensuring clean task completion. Asyncio creates separate tasks for each request without explicit structuring. Now let's look at differences in error handling. Trio and Asyncio offer different models to manage errors in concurrent environments. Trio integrates error handling into its structured concurrency model, aiming for clarity and predictability. Asyncio provides mechanism for error handling, but requires careful handling to manage complexities. Trio uses nurseries to ensure that errors do not escape the structured block of code. In the Trio example, the nursery catches and erases errors from child tasks to the parent block. Asyncio tasks must be explicitly awaited and handled for errors. It can lead to uncaught exceptions if not managed properly. The clearer propagation of errors in Trio model helps in maintaining a predictable flow and simplifies debugging. In contrast, Asyncio requires more careful orchestration to ensure errors are handled. Consider web application that needs to handle potential database query failures. In Trio, the structured concurrency ensures that any error in data fetching is immediately handled within the scope. This leads to cleaner and more maintainable error management. In Asyncio, each task must be individually tracked and handled for errors, which can complicate error management in larger systems. Let's look at the differences in design philosophies. Trio aims to simplify asynchronous programming through high-level abstractions. Asyncio provides a spectrum of APIs from low level to high level, offering flexibility at the cost of complexity. Trio's API abstracts away many low-level details, focusing on ease of use and reducing boilerplate. In the Trio example, the nursery context manager simplifies handling concurrent tasks. Asyncio offers both low-level APIs, like handling individual read-write operations, and high-level stream abstractions. This flexibility allows more control, but can increase the complexity and the potential of errors. This example demonstrates implementing a basic chat server using both libraries. Trio's abstraction allows us for focus on the core logic without worrying about the underlying asynchronous handling. On the other hand, Asynccio's approach offers the flexibility to optimize and tweak every aspect of connection management. Integrating asynchronous frameworks into existing codebase presents various challenges. Trio often requires significant adaptations due to its structured concurrency model. To integrate Trio, existing synchronous code must be structured around nurseries and task management. This requires a paradigm shift to structured concurrency, and it's impacting how tasks are created and managed. In contrast, adapting code to Asyncio often involves fewer structural changes, leveraging its flexible event loop and task model. This makes Asyncio more accommodating for gradual integration, where parts of project can be asynchronously enabled without overwhelming the entire system. True Asyncio is the library designed to integrate the structured concurrency of Trio with the flexibility of Asyncio. This combination allows developers to leverage the strength of both libraries within a single application. Trio Asyncio provides tools like Trio to IO and IO as Trio to convert functions between Trio and asynchronous flavors. This syntax allows asynchronous functions from both libraries to coexist within the same application. So this way you can use both Trio and Asyncio without refactoring the entire codebase. Next, we look at latest Trio updates. This section covers the new features of 2023 and 2024. Thread completion wait is an important feature to ensure that all threads have completed their work before completing operations. This feature is part of Trio's robust handling of asynchronous programming and multi-threading. It provides a safer shutdown by blocking tasks from executing until no threads are running. Waiting for thread completion is implemented using the trio.testing.waitAllThreadsCompleted function. This function blocks the execution of tasks until all threads spawned during Trio operations have completed their tasks. This example demonstrates how we can use it in multi-threaded server scenario. After exiting the main server loop, the method ensures that all client connections are properly closed. This function prevents from stopping while background tasks are still completing, thus avoiding resource leaks and potential data loss. Trio's adaptation of the pathlib library aligns it with Python's standard path manipulation tools. This feature provides a seamless and more intuitive approach to file and directory operations within asynchronous environments. Trio's path object is now a subclass of pathlib.purePath, allowing for natural integrations with other pathlib types. Methods like iterdir and readText are adapted to support asynchronous operations. The example on the left demonstrates reading directory contents asynchronously using Trio native path interface. So developers can now manage file paths using familiar pathlib patterns. Consider an application on the right that requires managing numerous project files across directories. Using Trio's path, operations like copying and moving files are handled asynchronously. We use the globe patterns to identify specific files and then copying them to a back application. Path-flip integration allows these operations to be non-blocking. Trio24 introduces new helper classes designed to improve testing of exception groups. The new test helpers, race group, and matchers play a key role in handling trio exception groups in tests. Races group is used to specify expected exceptions, functioning similarly to pytest.races, but for multiple exceptions. Matcher allows detailed assertion of exception types and messages within an exception group. This example demonstrates how Trio's testing tools can be applied in a network application scenario. Trio's latest update introduces enhanced type checking capabilities, utilizing type-aware tuple across key functions. Trio helps prevent common bugs associated with dynamic typing in asynchronous functions. The inclusion of type-aware tuple allows Trio to perform enhanced type checks on functions like trio.run and nurseries.startSoon. By applying these type checks, developers can catch type mismatches early in the development cycle. Consider the implementation of a type-safe asynchronous database query handler. Here we can ensure the function handling the query and its parameter are correctly typed. Trio23 introduces improvements in nursery exit behavior. This feature ensures that when exiting a nursery, the parent task always waits for children tasks to complete. The update ensures that parent task does not exit the nursery until all child tasks have completed, enhancing task synchronization. Previously, attempts to cancel this wait could lead to an injected cancelled exception, which Trio no longer does, avoiding unnecessary confusion. Consider a scenario where an application needs to manage multiple concurrent database queries. The enhanced nursery exit behavior ensures that all queries complete before moving on to data processing. It's preventing data concurrency issues. Trio23 brings improvements to how threads and tasks interact, especially in terms of context and cancellation propagation. These changes ensure that tasks running in threads behave more predictably and integrate seamlessly with Trio's main event loop. Trio's approach to thread integration involves preserving task context and undo state when transitioning between threads. The runAsync function is a key, allowing synchronous blocking function to run in a separate thread without blocking Trio's event loop. Consider an asynchronous web scraper designed to simultaneously fetch data from multiple URLs. Using runSync, we can execute synchronous HTTP requests in separate threads. It allows Trio's event loop to efficiently manage multiple requests. Trio23 also introduces refined capability in guest run initialization. This feature allows for immediate usage of Trio-specific operations post-initialization. Trio's guest run initialization now does more setup before returning control. It allows developers to use Trio-specific APIs like trio.currentTime right after initialization. Consider a scenario where Trio is used to integrate a synchronous database operation with external libraries. Guest run initialization allows for database connection to initialize through external libraries while using Trio to manage tasks. Trio 22.1 introduces the capability to name threads created with runSync function. It allows for easier identification and tracking of threads in complex applications. The thread naming in Trio is implemented via name parameter in runSync function. Imagine a complex application. There are multiple services run concurrently, each on its own thread. And by naming threads, developers can more easily identify and manage them in some system monitoring tools, or when analyzing logs. So we've learned a lot about Trio. Let's move to summary and the key takeaways. Trio makes it easier and safe to perform multiple tasks at the same time. We started with how nurseries and spawning work to create a safe task space. Then we looked at how Trio handles errors. We also learned about checkpoints that help manage tasks when they get busy. We talked about tools like semaphore and memory channels. We compared Trio to another tools, Asyncio. We also talked about the latest updates to the library. So finally, I just want to say thank you for listening, and also thank you to XtremePython for hosting me today. If you have any questions, feel free to ask now or contact me later. Enjoy the rest of the conference and see you next time.